All right, welcome back. We are going to talk about just-in-time topic number 2, properties of real numbers. We've superficially mentioned it before. I want to go into a little more depth. Again, some of this will sound the same. Some of it hopefully will give you a little new information. So commutative property, the numbers can commute. They can move around within the expression. I mentioned previously that it has to be all addition or all multiplication. You can't like mix and match in the middle and then move the things around and expect that it's going to be the same. So here I have my addition, which is A plus B equals B plus A. Here I have an example of 7 plus R equals R plus 7. And again, these are really simplified versions of materials, really simplified expressions. Only two things to move around. All of a sudden, though, you can go on and have much larger expressions and have to move things around within that. Now, here I have 9 plus n plus m, and we can move that 9 around. I have that 9 at the beginning, and then I have it middle, and at the end of that. And then we could have moved around the n, and we could have moved around the m. All of those, so there's more than just these three as an option here. I do want to just emphasize one thing before we go on to the multiplication piece. A times b, I have an a asterisk b, and then I have the a times sign b, and a dot b, and ab together. All of those are multiplication. Those are exactly the same statements. I try to remember to use a times b with the asterisk or ab because I don't want people to get confused with this being, is it a variable, or this thinking it's some other operation that maybe got cut off somehow. So I tend to do this try to keep it to those two types. That's not to say I never use the others, but it's generally speaking, those are the two that I use the most. So in my multiplication version of the commutative property, I have a 7x equals x times 7. Now just a word here. Both of these statements are exactly the same mathematically speaking. However, convention normally has us say 7 times x as opposed to x times 7. If you're working on a math problem and this is on your scratch paper, that's just fine. I'm totally good with that. I want to make sure, though, that folks know that when you get to that final answer, unless you want to look like you have a really weird math accent, you're going to want to have it in this format. You're going to want the number and then the variables, and you take the variables in alphabetical order. So here's a case where we have 5 times j times k, and my 5 can, again, be moved around in here, and I would have all exactly the same answer. I could move around the j here, I could move around the k here. They would all give me the same answer as long as I continued to multiply. It will become handy here once we actually start having to collect our like terms. So next up is the associative property. It determines which numbers do we associate first. And again, this is an addition case. There's also a multiplication case. So A plus the quantity of B plus C is going to equal the quantity of A plus B plus C. So sometimes it makes more sense to kind of do that addition one way over the other way because it makes it easier to think about or is simpler to solve. Again, I have 7 and E. Those two are added together as a quantity, and then we add F. Or we could have E and F as the quantity, then add our 7. All right. Here we have a case of more than just the three terms. We've got 5x plus 7y, and we're going to put that in our parentheses. And then we have a plus z plus 9. And I can change which ones I am grouping. And note here that I am not using the commutative property at this point. I am only changing the grouping. I wanted to be really clear what's actually happening here. So here I'm going to have my 7y plus z. I have to address that first, and then I come back here and do my 5x and add that to this quantity, and then plus 9. And here I would have my z plus 9. I'm going to have to address that, and then I would come back here and I do my 5x plus my 7y, and then that quantity. All right. Multiplication, same kind of deal. I have a times b. That quantity is multiplying c. And here I have my a multiplying the quantity of b times c. We can have 6w times x, or you can have 6 times the quantity of wx. Here we have one where it's 35 times xy. Z. You could have 35x and then yz. You can have 36x yz, and the grouping is the yz first instead of the 35x. And there's lots more opportunities to address that. Now, I want to show an instance where, at least to me, it makes more sense that you would group these numbers a little differently. These are all the same set of numbers. It's 8 times 3 times 2 times 5, each one of these. So this one and this one and this one are all exactly the same, and they're in the same order. Now I'm going to address grouping them a little differently. So here I have 8 times 3, which gives me 24. And then I have my times 2 times 5. Well, 24 times 2 is going to be 48 times 5. And I don't know about you, but if I have to do 48 times 5 in my head, I have to kind of stop and think about it a little bit, maybe write it down on some scratch paper. So this, to me, is not the easiest way to approach this problem. Here's another way to approach it. We have 8 times the quantity of 3 plus 2, which gives us 6. So I have my 8 times 6 is again going to get me that 48. And I'm multiplying by 5 in each case. Again, I've got my 240. Again, this is not the most straightforward or easiest way that I could see to approach this. This is the one that I personally prefer, because I'm like, okay, I can see that that 2 and that 5, I multiply that together, that's a 10. Multiplying by 10s are easy. So I'm going to go 8 times 3 times the quantity of 2 times 5. Well, that's going to get me 8 times 3 times 10. Well, 8 times 3 is 24. 24 times 10 is going to get me the 240. Now, did we get to the exact same set of numbers? Yes, we did. But sometimes grouping them a little differently, you can make your life a little easier. So sometimes it's worth taking a pause and saying, okay, what's the bigger picture here? Do I have to jump in and do it left to right, or can I use the commutative property and associative property to help me out? Okay, moving right along, we're going to have our identity property, and here's a case where we go ahead and add. I've got a plus 0 and 0 plus a equals a. Here I have x plus y plus 0 is going to give me back my x plus y in the end. Again, here I've got a case where I've got my 7h plus 3j plus 0 is going to get me my 7h plus 3j. Okay, up until this point, everyone's like, yeah, we all know that. That's obvious. Okay, here's where it's not quite so obvious, and this is where it gets to be useful. So I have 4r plus 9s plus m plus the opposite of m in that quantity, and that's going to equal my 4r plus 9s plus 0, because this and this are going to cancel each other out, and they're going to go to 0. So that goes to 0, and then I have my 4r plus 9s, and that's my solution. Instead of this big, long, clunky thing, I've got it shortened up to this, but I had to recognize that this m and the opposite of m are going to give me a 0 here. Okay? Again, multiplication, very, very similar. You can have 5 times s times t times 1. That's going to get me my 5st. That's not going to change anything. Here I have 8d times 7e times f times 1. And if I'm being asked to just address the identity property without actually solving anything, I can rewrite it to be this. I could have 8D times 7E times F. To get to the solution, however, you're going to need to multiply the two numbers here. I have my 8 times 7, that's going to get me the 56, and then my D times E times F. And that's again in my order of alphabet. You know, it's the alphabetical order on those. So I have 56 DEF. All right. Here I also have one where I have 9P times Q times 2 times 1/2. And this is almost that same sort of concept as, okay, I'm going to have something happen here to get these guys to go apart by addressing them kind of by my associative property of recognizing that 2 times 1/2 is going to get me a 1, right? I have 9P times Q times 2 over 2, which is really a 1. So 9P times Q times 1, which is 9P times Q. All right. So it tends to be something where you're going to have to stop and pause a moment and think, is there a way that we can kind of make our lives easier by considering this, and also keeping in mind that lumping things together in that way, like here we had that M and the minus M, or our 2 and our 1/2, those things are going to get us back to our identities. The inverse property, I've also mentioned that that's very similar and very much related to the identity property. Here we're going for the identity to be right there on our end instead of inside the equation. So here I'm going to have A plus the opposite of A is going to get me 0. So here I have a case, I give an example here. I've got -5 plus 5 plus x is going to get me 0 plus x, which is just x. Now, I want to point out, here's my A, and I've written it as a positive here, and then this is the opposite of A. That does not mean that my first number has to be positive. This is just fine. I can have a -5, and then the opposite of -5 is a +5. So this is not broken by using a negative number and then a positive number. Same sort of thing here. I've got my B plus C plus the opposite of B plus the opposite of C. And again, that's going to get us all to 0. So we're going to like match those opposites up with the original number, and that's going to get canceled out. So you're going to have like a B and a negative B are going to go to 0, and you have the C and the minus C going to -0 or go to 0. Here we have, and it doesn't have to be in the same order. I mean, I want to make certain that people are aware that it can be, the order can be juggled around a little bit. Here I have a case where it goes to 0. Here I have a -7 and an 8, and then I have a 7 and a -8. So again, you have that inverse property happening in the addition, and they will cancel each other out to go to 0. So for multiplication, and I'm going to just finish up this one piece, and then I'll come back and do the distributive property and from there on out. All right, so the multiplication, we've got P, which is the same as P over 1, times 1 over P. When I multiply those two fractions together, I get P over P, which is a 1. When I don't have just a solid number here, where I have already a fraction, it makes just as much sense to use that fraction and turn it on its head as it would be to put it over 1 and then have to deal with it. So I have 2 over 3x, and this, I want to be clear, this is part of the denominator. So then when I multiply, I'm going to multiply by 3x over 2, which gets me 6 over 6, which is a 1. And I have my UVW, and I'm multiplying that by the inverse, which is 1 over the quantity of UVW. And if that can feel a little intimidating. It's a lot starting to happen there. It can get a lot longer and become even more intimidating. But here I have, I'm able to pull it apart a little bit. I'm able to take that UVW. Remember, all I'm doing is I'm multiplying here. So I can stretch that out just a little bit, make it a little clearer that that's what I'm doing. And my 1 times U is the same as my 1 times U times 1 times over V, my 1 over W. I think I said that right. So my fractions of 1 over U, 1 over V, 1 over W, when I multiply them together, I would get 1 over UVW. So these guys are going to, again, cancel out to be a 0. All right? So there's a lot that you can think about and take away from this in how we're going to address solving things. If you really think hard about it, this is how we solve algebra problems all the time. We just haven't spelled it out quite this way. All right, I'm going to stop here, upload this, and I'm going to continue on with distributive property on the next film.